So just so that you understand how this paper 2 is structured, we are going to have a look essentially at questions 6 and 7 type questions today. So the trig functions and the 2 and 3D trig. All right, but before we get into that, I just want to discuss your parent functions. Okay, I don't know how well I'm going to be able to draw these. I'm going to do my best, but you'll survive. All right, so I'm not going to draw from negative 360 to positive 360. We know, or we should know, that these trig functions are symmetrical about both axes. So just bear that in mind. But like I say, knowing your parent functions, incredibly useful, incredibly important. This is all on Google Classroom in that info pack, but obviously I'm going to do it here. And so if you want to still take a screenshot later, you can. So I'm going to start with the sine function. So y is equal to sine of x. This is your parent function. So a parent function is one where no manipulation has occurred. We haven't changed a, we haven't shifted left or right, we haven't shifted up or down, we haven't changed the period. It's just a basic sine graph. All right, so your basic sine graph starts at the origin, has a peak at 91 or a maximum at 91, has an x-intercept at 180, 0, has a minimum at 270, negative 1, and has another x-intercept at 360. So your parent function of a sine graph, oh, it's not good. It's fine. Looks something like that. Okay. Now, the reason I'm saying know this parent function is because we then know that the sine graph can be manipulated. Okay, so we know that we can have a times sine of k of x minus p plus q. These four a, k, p, and q, those are all the manipulations of your sine graph. It'll be the same for cos and tan, but we'll get there. A changes your amplitude. So remember, this is where you can stretch it vertically or can squish it. A also, if A is negative, is a reflection. So it flips over your x-axis. K is your period change. So if there's a coefficient to the angle, it changes the period. It might make your cycle occur faster, or it might stretch out the cycle. This x minus p situation is a shift left or right. And Q is a shift up or down. So there are four manipulations that we have to know. But again, knowing your parent function, you can always relate it back to that and you can figure out what you need to. And the reason I'm saying that is because oftentimes they'll ask you questions like, if you manipulated your graph, what is your new range? And it's only for 2 marks. And now you're sitting there and you're trying to think, well, I don't know, do I need to draw this graph to try and figure it out? What do I need to do? No, because you know what your parent function is. Excuse me. So knowing, like I say, your parent function is very important. So that's for your sine graph. Your cos graph looks like a cup. I could draw. Obviously, I'm going to draw it in for you now. So your cos function starts at 1 and then decreases from there. So it starts at 1, has an x-intercept at 90, a minimum at 180, negative 1, another x-intercept at 270, and then it has another maximum at 360. So I always remember cos and cup. It sort of is a cup-looking shape. And like I say, just know where your maximum points are and know where your x-intercepts are and know where your minimum points are. Right, all of the same manipulations apply to cos. So I've drawn the graph of y equals cos x, but I can manipulate it in the same way. I can change the amplitude, I can change the period, I can shift it left or right, or I could shift it up or down. Tan is the unique one, right? It's a little bit of an oddball, but it's okay. We still love it. Tan now has asymptotes. So this is the one that we need to be careful of. Tan also, remember, has a different period to the rest of our functions. So cos and sine have a period of 360, period being the interval over which the cycle repeats. Tan has a period of 180. Excuse me. So tan has asymptotes at 90 and 270. Obviously, this also reflects over the y-axis, so there would be asymptotes at negative 90, negative 270. Every 180 degrees, we get an asymptote essentially. Right, your tan graph then has another very important point because tan doesn't really have an amplitude like sine and cos. Sine and cos, you can very easily measure your amplitude to figure out what's going on, but tan doesn't have that. Tan sort of looks something like this. I'm going to do my best to try and draw this as well as possible. So this is your tan function. This point at 45 degrees will determine for us our amplitude. So a normal or the parent function of tan has a point at 45, 1. This point here is at 135, so this would be at 135, negative 1, and x-intercept at 180. This would be at 225. Again, if we read up to 1, 270 is an asymptote, and then at 315. So that 45-degree 1 point is super useful for us to determine amplitude. Okay, so again, I have drawn y is equal to just tan x. That's just my basic parent function. But again, all of these manipulations can occur. I can change the amplitude. I can change the period. I can shift my tan graph left and right, and I can shift it up and down. I'm not saying always. So 2 years ago, the paper worked with a sine graph and a tan graph. Most of the time in trig functions, we are working with sine and cos graphs because sine and cos, because of their co-ratio relationship, do go hand in hand. So tan isn't asked often. However, it can be asked, and so you need to know it. All right, so please don't skim or skip out tan. You still need to know it. It's not asked often, but you do need to know it. All right, so these are your basic parent functions of your sine, cos, and tan graph. Like I said, learn them. Know what they look like. Know where their points of intersection are. Know where their maximum and minima are, because it will help you as you go forward. So I'm just going to wait in case anyone does want to screenshot this. Like I said, it is all on Google Classroom in that paper 2 info pack that I put on there. But if you want to screenshot it, do so. And then we're going to have a look at our questions, get into it. Okay. Give myself a lot of space. Okay, so you can see where the questions come from. I don't think I need to read that to you, but they are all from government provincial papers, so you can have a look at them if you want to, but obviously we're doing them together. So we have got, sketched below is the graph of f of x equals cos of x over 3 in the interval x element negative 180 to positive 180. So just a couple things. Remember, any trig graph goes on to infinity. So when we draw a trig graph, our interval is always limited, or restricted rather, that's the right word. We always restrict the interval because we cannot sketch to infinity. So we are being told where our start and end points are for this function. And we can see that indicated for us on our graph. The next thing, whenever you are given an actual function, so here we've been given f of x. Before you even get to the questions, understand first what is happening here. Okay, so this division by 3 is in my angle. Remember, this bracket is my angle. And so what this is doing is this is affecting my angle in some way. Now, if I wanted to rewrite this, I could have written this as f of x is equal to cos of a third x. That means the same thing. And so what we need to realize is that this a third is my k value. This is affecting the period of my graph. Right, now when your period or when your k value is a fraction, what it's doing is it's stretching your graph out. So rather than my graph completing its cycle in a normal 360 degrees, this a third is saying it now takes 3 times as long to complete my cos graph. So rather than my cos graph, this is not going to be drawn very well, so just bear with me. So rather than my cos graph completing its cycle in the first 360 degrees, what now happens is that it takes 3 times as long to complete my cycle for my cos graph. That is what the third says to me. So terrible drawing here. I do acknowledge that. I apologize. Just trying to get the idea across. And so what we've been given here, obviously this extends to the negative axis as well and would go like such. This portion of the graph that we've been given is this portion over here. Okay, so the sort of bump over the y-axis, sorry. Now that we know what we're working with, we can now go answer some questions. Okay, so it's really important that we do actually understand what has been given to us before we go and answer questions. Because if I just looked at this graph without understanding, my first thought would be this is not a trig function. This is a weird curve, okay? But it is a trig function, and we need to understand that it's because of the period change, we now have just this very weird portion of my graph. So this is before we even get into the questions. The first question asks me to draw the graph of g of x, which is sine of x plus 1, clearly showing all intercepts with axes as well as the coordinates of all turning points. You always have to show that stuff for any function. You know that. So this is now where the knowledge of my parent functions is super useful to me. So I know that a normal sine graph without any sort of transformation looks something like that. Okay, peak at 90. 1 to 70, -1. That's not a -1. Don't know what that was. -1. And then we have our x-intercepts at 180 and 360. So immediately me just knowing where all of those important points are, intercepts with the axes, turning points, I can now start to draw my graph. So who can remind me what this +1 is? What does that do to my sine graph? What effect does that +1 have? Right, good. Okay, so just be careful. A shift left or right would be in the brackets because that's affecting the angles. Because this is a +1 outside of my bracket, so outside of my angle, this is a shift up or down. So like I said, a shift left or right would be something like sine, and then I would put my brackets, let's say x plus 15. In the brackets, left or right. Outside of the brackets, +1, up or down. So just be very careful. Inside the brackets is angles, so shifting left and right, because remember left and right is on the x-axis, which is your degrees. The constant term outside that bracket is your shift up or down. Okay, so exactly as Bongyun Kosi said there on the chat, this is a shift 1 unit up. So guys, quite literally all I want to do is I want to take every single one of these points here of my parent function and just move everything 1 unit up. So rather than starting at 0, 0, I'm now going to start my graph at 0, 1. Rather than having a peak at 91, I now have a peak at 92. Rather than having an x-intercept at 180, I now shift that 1 unit up, and it's now at 181. And so I get the beginnings of my sine graph. Now, what I need to remember is that this continues on the other side of my y-axis. So this would carry on down. Usually my minimum would be at -90, -1, but we're shifting 1 unit up. So now it's at -90, 0. So I would usually, like I say, have a minimum at -91. I would usually have an x-intercept at -180, but now it's shifting 1 unit up. And so I've got the rest of my function. I've got my y-intercept at 0, 1. I've got my turning points at 92 and -90, 0. And obviously I've got my start and end points. Okay, so again, knowing your parent function, super easy. I know a lot of you use your calculator, and I'm not saying that's wrong. If you need to use your calculator, fine. But using your calculator takes time. It requires you to type everything into your calculator. It requires you to obviously then plot each point by point. If you know your parent function, it just makes life so much easier. All right, so again, fine, use a calculator if you need to. It's not the end of the world. However, if you can try and do it without, I promise you it makes life easier. Okay, so but now we've got our function. There it is, no problem. A nice 3 easy marks for us. So then we're being asked to write down the period of f. So remember, what we have just drawn is g of x. What we were given initially is f. Right, so there's a couple ways that you can do this. Obviously, you can just use the k value that we gave you earlier. So remember, period is determined by taking the original period of that function. So for cos, it's 360, and dividing it by k. So in this case, our k value was 1/3. So we would need to take 360 and divide that by 1/3, which essentially means you're timesing by 3. And so this tells me that my period of the cos graph of cos x over 3 is 1080 degrees. Makes sense. It's stretching out. It's going to take much longer to complete the cycle. And so the period should increase. It gives me a greater interval to then complete the cos graph cycle. So that little formula of 360 over k, very, very useful. You use that for sine and for cos because the original parent functions have a period of 360. For tan, you would just have 180 over k. That's the only difference. Right, obviously, like I say, if you can do that without the little formula, so for example, if you knew you just had to times your period by 3, that's absolutely fine. It's 1 mark, you can get a mark for the answer and that's it. But just know that if you're struggling, there is a little formula that we can use to determine our period of our trig functions. And that is your period, whatever the original period is, over k. All right. The second question, 6.2.2, says the range of g of x minus 3. So g of x was the sine graph that we just drew. Sine of x plus 1. But now what we need to bear in mind is that there's an added minus 3. You quite literally just add that onto your equation. Okay, this is essentially telling me that I'm taking my original graph g of x and I'm shifting 3 units down. And so we now need to figure out where this graph would sit if we shifted 3 units down. So this would now give me sine of x minus 2. Now again, if you can visualize this in your head, wonderful, great. If you can't, again, this is where your parent function comes in. If we have our sine graph, I know I'm drawing a lot of parent functions here, but it really is super useful. So if you've got your sine graph there, this is just a normal sine graph. This minus 2 is telling me that I need to take this graph and I need to shift it 2 units down. All right, so we would now take our sine graph and we would do exactly that. It's very aggressive. I'm fully aware of that. Sorry, let's just make it less aggressive. Okay, so we're going to take the sine graph and we're going to shift it. So this now has to move 1, 2 units down. So again, this is my normal sine graph, 1, 2 units down. That's all I need to do. And so again, we now can just move all of those points with it. Now the question said the range. So technically I actually only care about the maximum and the minimum because range is your y values. So normally your maxima is at 91, and your minimum at 270, -1. And we just move those 2 units down. So this is not a great rendition. 1, 2. So this is now at 90, -1, 1, 2, This is now at 270, negative 3. And so these new y coordinates become the range of my function. So negative 1 and negative 3 will determine the range of this graph. Now we always start from the smallest value, so negative 3. And we go to the biggest value, negative 1. Range is y. And we put in our inequalities. We can include negative 3 and negative 1 because at those points we do get turning points, so the graph does exist there. And so we have the range of g of x minus 3. So once again, grade 12s, knowing your parent function, incredibly useful to you. All right, and for me, like I say, oftentimes when I am answering trig function questions, I constantly am drawing my parent function and then manipulating it according to however I need to manipulate it, just because it just makes life easier. Rather than you now having to, once again, use your calculator, use the table method, draw the graph, try and figure it out, it just helps shortcut the whole process. All right, so it's going to get quite small otherwise. Let's screenshot what we have so far and then we'll carry on. Obviously, guys, remember, if you've got questions, you just ask. Okay. So 6.3 says determine the maximum distance of g of x minus h of x, where h of x is the reflection of g in the x-axis in the interval x element negative 180 to positive 180. So remember, g of x was our sine x plus 1. Okay, so again, if I just, obviously we've got the graph up there, I just don't want to keep scrolling back and forth. Negative 180. So our graph that we drew was the blue one. I'm just going to get it right. She said with absolutely zero confidence. Oh, that was a much better graph. Okay, so there's G. It is now asking us to look at a distance between two graphs. But before we do that, let's understand what actually H is. So H is the reflection of G in the x-axis. So basically, I'm going to take this graph of G and I'm going to create the mirror image over on the other side. So this is then going to look something like this. And that is the mirror image H. Out of interest, your equation, when you reflect over the x-axis, you make the whole y value negative. So this would be now minus sine x minus 1. Okay, you just times your y by negative 1 when you reflect over the x-axis. So we now know what h of x looks like. And it says determine the maximum distance. Now, the order in which we subtract is very important. G of x minus h of x. So essentially, this is the distance where g of x is on top of h of x. So g of x must be the top graph, and then we look at the maximum distance down to h of x. Now, because I've done this beautiful little sketch here, I can see where the maximum distance is going to be. It's going to be between this maximum of g and this minimum of h. And so if we were to then go and determine what that distance is, it's now very easy because we have the sketch. We knew from g of x, because we've obviously already done it, this is a maximum of 92. And because of the properties of a reflection, this is now at 90, negative 2, which means that this maximum distance between these two graphs is 4 units. 2 units here, 2 units here. And so it's a maximum of 4 units. Right, so a question like this does look scary. It does look a bit weird and a bit frightening, but understanding what's happening, very important. And again, use a sketch to help yourself. There's nothing wrong with that, okay? We're not saying you may not use sketches. Use it. If it's helpful for you to visualize what's happening, that is what you need to do. Okay, so maximum distance, 4 units because it's from the maxima to the reflected minima. Right, 6.4 then says for which values of x in the interval x element of negative 180 to 180 will f of x times, I'm going to be honest, I'm not sure if that is that's a mark or not, now that I'm looking at it properly. Sorry, guys. I did not notice that in the 3 or 4 times I've had a look at this. I think it's a dash, so a derivative. So let's just make sure. Yeah, that's a dash, right? So that is a useful piece of information. Sorry, I don't know how I've looked at this multiple times and did not click that there was a little dashy dash there. Okay, so we're going to talk about this now because, again, this is what would throw us off. So it's asking us where is the product of f of x, so remember this weird looking cos graph, and the derivative of g of x greater than 0. Now already we're thinking the derivative of a trig graph. What on earth? Okay, we know how to work with derivatives of parabolas and straight lines and cubics. That's great. But of a sine graph, no. All right, but we'll go back to what this all means now. Firstly, if we want our product to be positive, so this here is saying a positive product. The only way for us to get a positive product is to say a positive times a positive, or to say a negative times a negative. That is the only way for me to do that. Now, if we look at f of x, hopefully we can all agree that, and remember, positive, negative, these are all my positive y values. These are all my negative y values. So that is what I mean when I say positive, positive, negative, negative. Hopefully we can agree that for f of x, the whole graph is positive. Okay, for this given interval, the entire thing that I have here is positive because the whole graph sits where y is positive. So that's cool. What we now need to deal with is this derivative situation. And this is where we just need to go back to our basics of calculus. Remember, a derivative gives us information about the gradient. Okay, so let's think about this clearly. If I need to take a positive, which I know f of x is positive, I need to find out where this gradient is also positive, because I know that my product must be positive. So f is already only positive. So the only way for me to get a positive product is to times it by another positive. So I want to have a look at my sine graph, and I want to have a look and see where my gradient of my sine graph is positive. So let's go have a look. Always read left to right. This is a negative gradient, so that's not going to work for me. Obviously, negative 90 is a turning point. That's where our gradient is 0. We don't want that. We want it greater than 0. But now, between that turning point and my next turning point, m is positive. I then get to my turning point, m is negative, and then my graph starts to decrease again. So essentially what I'm looking at here is this little section in the middle, because this is now where I have a positive times a positive. And we can really easily see what those x values are. So we can read off our x values. It's between negative 90 and 90. So even though the derivative thing is a bit weird and a bit scary, again, don't let it throw you off. Derivative is gradient. Look at where the gradient is positive or negative depending on the inequality you've been given. So we will only get a positive product between negative 90 and positive 90. The other gradients are negative, and so a positive times a negative, that doesn't give me a positive product. All right, so guys, really important. When there is a derivative, and they do like to throw this in, they also like to do it in paper 1. where they give you an inequality like this, but they ask you for a derivative product, just remember derivative means gradient. Okay, and so we're looking then where the gradient is positive or negative. Right, so let's take a screenshot of those two. It's a lot. I know a lot of screenshots, but it's all right. Lorato?
Hi, ma'am.
Hi.
So, ma'am, because the gradients for the turning points, they don't work, this means that, like, we don't, on the intervals, we don't include. Okay.
Yeah. So if this inequality had said greater than or equal to 0, then it would be fine, because here at our turning points, our gradient is 0. But it hasn't said equal to 0, so we mustn't include them. Cool. Right, so 6.5 says the graph of g, so once again, g is our sine x plus 1, undergoes a transformation to form a new graph, k of x equals sine of x minus 15. Describe in words the transformation from g to k. Right, so just quickly, just because we spoke about it earlier, I can now highlight this again for you. Because this x minus 15 is happening inside the bracket, this is affecting my angle, and so this is now a shift left or right. Can anyone tell me if it's gone left or right? X minus 15, is that 15 degrees to the left or 15 degrees to the right? Navashni, nice. Okay, so this is 15 degrees right. Remember, it's always the opposite sign that we would usually assume. Usually we would assume negative is left, but it's the opposite. Okay, so guys, again, don't panic about these sorts of questions. Essentially, set it up for yourself as a transformation. We're going from g of x, which is sine of x plus 1, to k of x, which is sine of x minus 15. And basically, all you do is you ask yourself, how is this equation changed? So the first thing that I see is that I've got no constant. All right. And so basically what that means is in order for me to get rid of that positive 1, I would have to subtract 1. And we know that a subtraction of 1 means a shift 1 unit down. So that's the first transformation that has happened here. The next thing that I notice is obviously to do with our angle. Initially in g of x, we just had sine of x. But now we've got sine of x minus 15. And we've already discussed what this transformation is. This is a transformation 15 degrees to the right. And so when it says describe in words, the words that you would write down are quite literally what we have here. Shift 1 unit down and shift 15 degrees to the right. That's it. So always compare your equations that you have and see how they've changed. The change is the shift, or is the transformation rather. Whether it's a shift left or right, an amplitude change, a period change, whatever. Do your comparison, see what has changed and how you got there. So like I say, that plus 1, in order for us to get rid of it, we would have to go minus 1. And so that's a shift 1 unit down. So comparisons, very, very important in trig functions. Whether you're comparing to your parent function, whether you are comparing equations, very, very important to be able to compare. Oh, sorry guys, something in my eye. All right, so let's just take this last screenshot and then we'll have a look at the next question. Lorato?
Ma'am, I have a question. So, ma'am, if they were to give us a transformation question, is it possible for them to ask, maybe let's say they go, the graph of g undergoes a transformation to form a new graph, k of x, whereby it's equal to 2 sine x plus 1. If it were to like be a question, how would we now describe it?
Okay, so let's go j of x. You said 2 sine x plus 1. Right, so again, compare. The plus 1 is still the same. So that hasn't changed. So it hasn't changed its shift up or down. So that's the same. What has changed, though, is this coefficient. Because initially our coefficient was obviously 1. So this was initially a 1. But now it's gone to 2. So this is an amplitude change of 2. So you just say that the amplitude has changed. If it was a negative 2, you would say an amplitude change, but also a reflection about the x-axis. So it's more likely that we do a negative rather than just 2. It's more likely we would say negative sine x to test whether or not you understand that that negative is the reflection.
Okay, thank you, ma'am.
Pleasure. Alrighty, so let's have a look at a 3D trig question. So again, grade 12s, I get it. Like I look at these sometimes as well and I'm like, no, but it really isn't hard. Okay, so we're going to read through the question, then I'm going to chat about some things that we need to look out for, and hopefully that'll help. Because once we start doing it, you're going to see it's actually not tricky. The algebra is not nice because the numbers we work with generally aren't very nice, but it's not tricky. Okay, it's not hard. So it says in the diagram below, TP, I'm going to scribble as I go, I'll take it all off. TP is the height of a building. The foot of the building, so this is the base of the building at P, and points QR are on the same horizontal plane. So what you almost need to imagine is your building, and then you almost need to imagine like a shadow on the ground. When it's saying the base, and this is on the same horizontal plane, okay, excuse how terrible this is about to be. I'm just using what I have. Here's your building, okay? No, I take that back. Let's do better. Here's your building, okay? There's my building. It's saying this is on the same horizontal plane. So this triangle in gray, I'm pointing to the screen as if you can see what I'm pointing at. That triangle in green is this flat bit here. But the base of my building and this gray triangle, they're on the same horizontal plane. Okay, so this is the ground. This is my building. That's what we need to start imagining. Okay, terrible demonstration, but hopefully that made sense. From angle, or from Q rather, thanks Layla. From Q, so remember this is the ground. From point Q, my angle of elevation, so up to the top of my building is 60 degrees. And then it gives me that PQR is 150. I can see that on my diagram, and QPR, I feel like I said the same letters, but let's try that again. PQR is 150 and QPR is X. It then also tells me that the distance between P and R is 300 meters. So from the base of my building to some point somewhere on the ground is 300 meters. So I think what confuses us with this stuff is the whole 3D situation. But always just imagine it, and they will always color in or like shade in the ground. So you can always imagine it as such. There's my building. Here's the ground. Now remember, ground and building are perpendicular to each other. So you can see there the 90-degree angle because it has to be perpendicular. Right, so now we have all of this. We can now go answer our questions. So the first question says, write down angle R in terms of X. So we just identify where angle R is. There it is. And it's saying in terms of X. So what that means is this X needs to feature somewhere in my working out. And if we just look carefully, we have a triangle. Technically, we have two angles, 150 and X. And so we can just use sum of angles in a triangle to work out what R is. So R would be equal to 180 minus X plus 150. Sum angles in triangle. And so R is equal to, sorry, terrible angle symbol there. Let's try that again. R is equal to 30 minus X. That's it. All right, so again, don't panic when you get these questions. Read it carefully, go slowly, and you'll be absolutely fine. Right. I like to, Loretta, do you see your hand? I get you now. I like to, as I figure things out, I like to write it on my diagram. I know that the stuff I do at the start of my question is going to help me later. So I know that knowing that this angle is 30 minus x is going to be helpful to me at some point. So I'm just going to put it on my diagram because then I have everything in one place that I can refer to. Lorato, sorry.
Ma'am, so when it comes to like these questions, is it necessary to put in a reason unless they, like, when they don't ask for it? Because I see it's like 1 mark, so I'm just like, should we, or is it possible to just leave it out?
So technically no, because this isn't a geometry question. I feel quite strongly you should always put reasons because there is a reason why we've done it. However, no. So if you look at the marking memo for this, the memo itself doesn't even have the reason. So no, it would be the same as if you used a geometry reason in like analytical geometry or analytical geometry. You don't really need to put the reason there. I always do because that's who I am as a person and I'm okay with it. But no, like you say, it's 1 mark and the 1 mark is for saying r equals 30 minus x, not for the reason.
Oh, okay, ma'am. So even if it's like maybe also like a 3 mark question or anything, if they don't specifically tell you to put a reason, you don't have to. It's an optional thing.
So, I mean, again, it would depend what the 3-mark question is. Again, if it's not a geometry question, so if it's not the Euclidean geometry questions, we're not really going to give you marks for the reason. However, my advice is always write down the reason. But yeah, no, if it's within the 2D, 3D trig, no, as much as it hurts my soul to say it to you. Okay, right. So the next question says determine the length of PQ in terms of X. So again, we just identify where PQ is. And I don't know if you guys remember, this might have been one of those things where I had this conversation in my head and not actually had it with you. So we'll just see. The side joining your two triangles that you have, okay, is often important as well. So oftentimes this joining side, we're going to need to at some point work out its length in order to figure out questions later on. So even if the question doesn't lead you to it, 9 times out of 10, you're going to have to. So in this case, they've scaffolded and they've asked us to actually find PQ. But you're going to see in the next question after this, knowing what PQ is useful. So this joining side, very, very useful, very, very important to find. So what we need to bear in mind is when we are looking for this adjoining, I'm sure that's a word, adjoining side, we need to take stock of what information we have. So firstly, I've got 2 triangles. I've got this non-right angle triangle down here at the bottom, and I've got a right angle triangle TPQ. However, it would be great. Oh, golly. It would be great if I could just go into TPQ, because then I'm just working with normal sine, cos, tan ratios. Lovely. However, I don't have any information in that triangle except for the angle of 60 degrees. I do not have enough information to work out PQ. So unfortunately, what that means is I'm going to have to work in this triangle PQR to go and find PQ. Now, because PQR is not a right angle triangle, we need to go to our sine, cos, and area rules, which, as I'm saying it now, would have been very useful for me to put on here. Let me just quickly grab them for us. Obviously, now I'm panicking, as I do. Right, here they are. Sure, they really squish these formulas in for you. Okay, so here are our sine, cos, area rules. I'll go through them now, which is which, but hopefully we do know. Obviously, this last one, area rule. The one with the fractions, sine rule. We also know it's a sine rule because it contains a whole bunch of signs in it. This one over here with the cos rule. Okay, again, in that little info pack that I put there on Google Classroom for you, I've explained when you can use each of these rules and what information you would need to use each of these rules. And so we're going to have a look at that now. So for your sine rule, essentially what you need is a pair. So when I say a pair, you need a side and the angle opposite it in order for you to use your sine rule. For the cos rule, you need two adjacent sides and the angle in between. That's it. So if we go back to what we're looking for PQ. So we know that some way PQ must feature in my equation or in my formula. If I look at the information I have, and remember we've just worked that out, I have got the angle opposite PQ. So that's great. It forms one of my ratios in a sine rule. And I have the 300 and the 150. So I've got a complete pair. So that means I'm going to use my sine rule. I need to have one complete pair, and then I either need to have the angle or the side of the other pair in order to determine the unknown. So here I can work out or work this. I can do my sine rule. So I always start by putting the side or the unknown that I want in my numerator. Remember, the sine rule is quite cool in that if you're looking for the sides, you put it in the numerator. But if you're looking for the angles, you can put those in the numerator and the sides in the denominator. It's a ratio, so it can flip either way. It really doesn't matter. Because it's a side I'm looking for, I put that in my numerator. And then it goes over sine of the angle opposite PQ. So this would be over sine of 30 minus x. That's the angle opposite it. This is equal to, my other side that I have is 300 over this angle opposite, sine of 150 degrees. And so what we now need to do is solve for PQ. So I am going to multiply both sides by the sine of 30 minus x, because I no longer want that on my left. Get rid of it. And so now we know that PQ is equal to 300 over sine 150 times sine of 30 minus x. Now, go tell us, bear in mind, you can actually type this fraction into your calculator. So this 300 over sine 150, you can simplify. That can be typed into your calculator and you can simplify that situation. So if you do that, that gives you 600. And so we get PQ is equal to 600 times sine of 30 minus x. And my recommendation is always to simplify what you can. It just makes it easier to work with because you're going to have to work with this later. Right, so now we know PQ is 600 times sine of 30 minus x. Again, I fill in what I figured out on my diagram. It just helps me know what I'm working with. All right, so I'm just going to make this a tidbit smaller so that we can take a screenshot now, and then we'll have a look at the next question. Okay. So if we look at the last question here, it says, hence show that TP is equal to 300 times root 3 times cos x minus root 3 sine x. So I would look at that and I'd be like, no, thank you though. It's nice of you to ask, but no. But again, we can do it. We will do it. We have this. All right, so I've just put the diagram down here for us again. Identify what side they're asking you to find. So TP. TP is essentially the height of my building. And because we're now in this right angle triangle, go back to your basics. whenever you are in a right angle triangle, you just work with your basic sine, cos, tan. Okay, there's no need to introduce sine rule and cos rules and area rules and all of that nonsense. It's just a normal right angle triangle. You can do it with the sine rule and the cos rule and the area rule and all of that nonsense, but that does overcomplicate things. So you can, but there's no need. Right, so we were given the angle 60. So here's my reference angle. It's 60 degrees. I've written over it, so I'm just going to rewrite it. I want the opposite side. I have PQ, which is my adjacent side. So guys, which ratio works with the opposite and adjacent sides? Which ratio works with the opposite and adjacent? So sine, cos, and tan, which one? Nice. Okay, so I don't know how many of you remember this. SOHCAHTOA, sine, opposite over hypotenuse. CA, adjacent over hypotenuse. TOA, opposite over adjacent. So this is how I learned my trig ratios when I was at school, SOHCAHTOA. And because it's opposite and adjacent, I'm going to work with tan. So tan of that reference angle, 60, is equal to opposite, TP, over adjacent, PQ. Now, obviously, guys, remember, we've just worked out what PQ is. So we can substitute that in. However, you can do it now if you want to. Personally, I like to... It's okay, Lorato, we all make that mistake at some point, I'm sure. I prefer to first isolate TP. The reason is if I now substitute in the 600 sine of 30 minus x nonsense in my denominator, I'm just giving myself more to work with. Okay, so I like to first isolate, simplify what I can, and then I'll substitute in. So to get TP alone, I would times both sides by PQ to get rid of it in my denominator. And so what I have is that PQ times tan of 60 is equal to TP. Now I've got TP alone. Now I can start substituting and simplifying and all of that. Now tan of 60 is root 3. So we've got root 3 times PQ, which is 600 sine of 30 minus x is equal to TP. Let's just fix that bracket. So remember, tan of 60, you can type that into your calculator, you get the ratio root 3. And now we've got that. So now our goal is to make this situation look like this situation. So now I need to, it's almost like proving an identity. I want to prove that those two things are equal. So now I need to start thinking, okay, somehow I'm going from only having a sine ratio to having both a sine and a cos ratio. So now I need to think, oh gosh, okay, how am I going to do that? Well, and obviously again, I should have put this here, but I didn't. Choices were made. This is now where we need to think about our compound angle formulae. Just put it on our actual lesson. I'm not going to let this frustrate me. I'm not going to let this frustrate me. There's no point. Okay. Don't let it frustrate me. I'm winning in life. Okay. There we go. So, again, we're trying to get them to be the same. This sine of 30 minus x, that's a compound angle. Sine of 30 minus x, this is a compound angle. Sine of alpha minus beta. If I go and expand that using my compound angle identity, I'm going to introduce that cos that I need. Because remember, I have to have a cos in what I'm trying to prove it's equal to. So this is how I'm going to get my cos in there. So we are going to expand. I'm just going to have to write this a bit over. We're going to leave the root 3 there. We are going to leave the 600. So I don't really have a problem with either of those things. I can sort them out a bit later. And now we're going to expand. So we will have sine of 30 times cos of x minus cos of 30 sine of x. So not particularly nice to work with. However, I now have those causes I wanted. And if you look here, more specifically and more importantly, I want cos x. There's my cos x, right? So now at least I have that. Sine 30 and cos 30 are special angles. So again, I would go and simplify what I can. Again, I'm just going to leave the root 3 and the 600 here. I can simplify them later if I need to. So sine of 30 is a half. So a half times cos x minus cos of 30, which is root 3 over 2 times sine x. And again, I want a sine x, and I've got the sine x equals TP. And now, if you think about it, both of these denominators are 2. So you could take half out as a common factor. Just understand that you're dividing everything by 2. There's a common denominator. And so what we can do is we can go and simplify. 600 divided by 2 is 300. Look at this. There's my 300. There's my root 3. Here's my cos x. Here's my sine x. There's the numerator left, root 3. I've got everything that I want. Okay, I'm going to take all of those beautiful squiggles off now because let's not overcomplicate the situation. So now I've got cos x, because remember I essentially divided that half away, minus root 3 sine x equals TP. And essentially what I've done is I've proven that this is equal. Obviously, you can go and write the 300 in front of the root 3. It makes no difference. These two things are being multiplied. An order of multiplication isn't important. And so we've proven that TP is in fact the expression given to us. All right, so when you are trying to show something and you are having to introduce things like we needed to introduce the cos, always go back to, is it a compound angle, is it a double angle, etc., etc. See what you can substitute in order to introduce the ratios, the term, the whatever, in order to get it equal to each other. And this is what I was saying earlier, grade 12s. Trig, as we already said on Monday, once you've applied your identities, whatever it may be, it's algebra. Okay, so the whole half thing, dividing, simplifying, that's all algebra. That's all just basic math skills that you have because you've been doing it since grade 6, grade 7, grade 8. So just don't overthink it. Do it methodically and logically. Remember all your identities that you can apply. And like I say, always go back to what it is you're trying to prove. We need to end up with all of those elements. So ask yourself, how can I get those things? The first question I asked was, how could I get cos? That's what led me to the compound angle formula. Then we could see, okay, cool, we had special angles. We can simplify all of those things. All right. So let's take a screenshot of this. I think you've got a screenshot of the other ones, but obviously you can tell me if I'm wrong. I'll just go to 7.2 just in case. And then let's have a look at the next one. All righty. Right, so we have been given the graphs of f of x equals sine x plus minus 1, and g of x equals cos 2x are drawn for the interval x element negative 90 to 360. Graphs f and g intersect at a, b at 360 negative 1 is a point on f. So that's the information we have. We can see all of that there. We're not having to sketch anything. It's lovely. All right, now what we do need to bear in mind is as much as they've given us the x coordinates, they haven't given us any y coordinates. And so this is where your knowledge of the parent function becomes important. The y coordinates deal with amplitude. Now, a normal amplitude for a sine graph is 1. The coefficient to your ratio tells you what the amplitude is. So because both of those coefficients are 1, it tells me that your amplitude is 1. So if we look at the sine graph G, not the sine graph, the cos graph G, this is a maximum at 1 and a minimum at -1. Sine would usually also be maximum at 1, -1, but it's obviously shifted 1 unit down. So this is now at -2. So again, knowing your parent functions, very useful because now you have a whole bunch of points that you know. So the first question asks us, write down the range of f. So f is this graph over here. And I want the range, which is all the y values where this graph exists. So can someone tell me what the range is for f? What is the range of f? Nice, Bongi and Corsi. So just remember, we always put the smallest number first. So your values are perfectly correct, but we just need to remember that we will write it with -2 first and then 0. So it's always the smallest number first. All right, square brackets, because we do have a point at -2 and we do have a point at 0. Obviously, if you would rather write it in interval notation, this would be it. I prefer interval notation, but it honestly makes absolutely no difference. All right, so that is our range of f. Nice and easy, no stress. So our next question says, let's do this. Write down the values of x in the interval that's given, -90 to 360, for which the graph of f is decreasing. So again, the green graph that I've highlighted, I want to know where the graph is decreasing. So take a look, have a think, and then tell me for which values of x you think it's decreasing. So where is f decreasing? Nice, guys. Well done. Okay, exactly. Between 90 and 270. This is increasing. Here we are decreasing. Then we start to increase again. So our x values are 90 and 270. So again, you can write it interval notation, inequality, whatever your heart desires. If you wanted interval notation, remember it's asking where it's increasing. So not where is it equal to 0, where it's increasing. So round brackets, 90 to 270, or your interval notation, inequality, 90 to 270. Either one, absolutely fine, completely up to you. Just remember, guys, we spoke about this the other day. Often these inequality questions, even though it's 2 marks, it's not a case of, okay, cool, you got the greater than 90 and the less than 270. It's an all or nothing. So you get 2 marks correct or 0 marks incorrect. Even if half of it is, even if half of it is correct, it's still 0. Okay, so just don't make silly mistakes with brackets or inequality signs or wrong order, whatever. Think very carefully about it, because this is 4 marks, which doesn't seem like a lot in a 150 mark paper, but 4 marks is an extra 4 marks. So don't make a silly mistake when writing it down. Right, I'm just gonna do that so you can screenshot, because the next question is quite lengthy. Right, so this question again is asking a length sort of thing. Length sort of thing. It's very mathematically put. So I'm just going to do that so that we can still look at the graph. So it says P and Q are points on graph G and F respectively, such that PQ is parallel to the y-axis. Okay, so let's just imagine what that means. PQ parallel to your y-axis, and it says PQ lies between A and B. So here's A, here's B. P is on G, so somewhere here. We don't know where exactly. And Q is on F. For it to be parallel to my y-axis, it has to be a vertical line. This is not parallel to my y-axis. It is asking me to determine the value or values of x for which PQ will be a maximum. Essentially, where along here between A and between B will this length between P and Q be the longest, the maximum length? Navashni, I'm going to be honest, I have no idea what you mean. So can you just help me out? Lorato?
Ma'am, I think they're talking about when you did the interval, is it x to the element or y to the element? Or 6.2?
Oh, sorry. I'm just living my worst life. Yes. Sorry. 6.2 is x in the element. I don't know why I wrote y. I do apologize. Thank you. X. I do agree. Thank you, Navashni. Get it? I'm now there. Right. So PQ, somewhere between these two graphs, I want to know where it is at its maximum length. So guys, the first thing to remember is any vertical distance is determined, particularly when we're talking about graphs or functions, by taking the top function and subtracting the bottom function. If it's just between 2 points, top y value minus bottom y value. So what this means is that the distance PQ, whatever it may be, would be found by taking my top graph, which is G, which was cos 2x, minus my bottom graph, which was sine x minus 1. This expression, when I go and subtract those two things, will give me the distance PQ. So if I just simplify the situation, cos 2x minus sine x plus 1. And I now need to go start figuring out what's happening here. Now, again, maximum kind of rings a bell of calculus to us. And I suppose if you're some sort of genius, you could, but calculus and trig, we try and avoid that where possible. So what we need to think of that is that a maximum, particularly if we have a quadratic expression, would be the turning point of that quadratic. Now remember, you've got a double angle here. We have double angle formulae. I'm just gonna, obviously it's gonna fight me. So let's just take what we need. So one of our cos double angle formulae deals with squares. So if we have a look here, we've got a cos squared minus sine squared. We've got 1 minus 2 sine squared. We've got 2 cos squared minus 1. If I were to replace this cos 2x with 1 minus sine squared, 1 minus 2 sine squared rather, then I have a quadratic. I've got a sine squared, a sine x, and a constant. Quadratic, turning point. I can work out the maximum. So I'm going to do exactly that. Cos 2x, I'm going to replace with 1 minus 2 sine squared x minus sine x plus 1. Again, here's my quadratic. Okay, let me simplify first, and then I'll show you what I mean. Minus 2 sine squared x minus sine x, and 1 plus 1 is 2. Quadratic, ax squared plus bx plus c, ax squared plus bx plus c. This is a quadratic expression. Yes, it's a trigonometric quadratic expression, but a quadratic expression nonetheless. And so now we use that knowledge. We know that if we go and work out for sine of x, because that is the ratio I'm working with, I essentially want the turning point. And we know the turning point is minus b over 2a. I can substitute what I have. Here's b, minus 1. Here's a, negative 2. So minus negative 1 over 2 times negative 2. That gives me negative a quarter. So this is telling me where I can find my maximum point. And from there, I know that as long as sine of x has a ratio of negative a quarter, I'm going to find my turning point, my maximum. Now, this is a very basic equation that we can go and solve. Wait. I don't know why I'm panicking. We need our reference angle. So we would type shift sine of a quarter into our calculator. Remember, you ignore the sign. So shift sine of a quarter is 14,477, etc., etc. We then look at the sign to determine our quadrant. It's negative. So cos sine is negative in quadrants 3 and 4. So quadrant 3 solution would be x equals 180 plus our 14,477. Now we can add the plus k times 360 if we want to. But remember, we were given a specific interval. So I can't really get a whole bunch of different solutions. It's within an interval. So you can add the plus k 360, but it's not necessary because of the interval we're working in. And so we get one solution of x is equal to 194,48. Okay, we'll check our solutions now in a second. In quadrant 4, our solution would be 360 minus 14,477, etc., etc. Again, you could add the plus k times 360, but because we have a restricted domain, we don't need to. And so we get that x is equal to 345,52. And so remember, point A and point B, that's where my solutions lie. Both of these solutions lie in that interval. 194 is somewhere here. 345 somewhere here. So at these points, I will have a maximum length of PQ. That is what the solution is saying to me. So again, guys, not a particularly hard question, but it does draw on knowledge that is very much boxed in our minds as paper 1 knowledge, the whole turning point minus b over 2a situation. And we've seen a couple times already as we've gone through our revision, every now and then we bring in a concept from paper 2 or a concept from paper 1. The other day we had one when we did our functions revision and there was an angle of inclination question. That is a paper 2 concept. That's analytical geometry, but we can bring it into paper 1. So always just remember, yes, you are studying for paper 1 and paper 2, but your general sort of overview, your general knowledge of your maths is incredibly important. We can't just ignore other information that we've learned. As I've said, paper 2 is very much algebra. You're using algebra throughout analytical trig and Euclidean geometry. So, excuse me, we need to still remember knowledge that we have from prior sections. Calculus as well pops up every now and then. We saw that earlier, the derivative graph. Understanding derivative is gradient. So don't completely block out paper 1. Don't completely block out paper 2. Always work with everything in conjunction with each other. Alrighty. Okay, so you can take a screenshot Oh, excuse me. I don't know if we're going to get through the full next question, but let's see how we go. Anything's possible. Okay. So this was their 3D trig question in 2019. I will say this, guys, and you can disagree with me if you want. I do think papers prior to 2020, so prior to COVID, are a little bit harder than 2020 to 2023. So please don't only look at papers from 2020 to 2023. Go back to like 2017, 2018. I do feel like there were some tricky questions in some of those papers. And I do think that we are heading back to that standard. So it is really important that you do go have a look at those types of papers. So for example, if you compare this 3D diagram to this 3D diagram, the one we did earlier is so much simpler in comparison to what's happening here. So just try and do a broad range of past papers. That's all I'm saying. Okay, I think we might get through a question here, but let's see what happens. The diagram below shows a solar panel, A, B, C, D, which is fixed to a flat piece of concrete slab. So I'm just going to do this. So here's our solar panel, A, B, C, D. A, B, C, D. Which is fixed to our flat piece of concrete slab, which is the gray blocky at the bottom there, E, F, C, D. That's already been sort of highlighted for us at the bottom. A, B, C, D and E, F, C, D are two identical rhombuses. I'm pretty sure it's rhombi, but whatever. Important. K is a point on DC such that DK equals KC. So we can see that indicated to us on our diagram. Remember the little lines. So these are strike marks. Means that line segments are equal to each other. And we've been told that AK is perpendicular to DC. Again, we can see that. AF and KF are drawn. Angle ADC is equal to CDE, which is equal to 60 on our diagram. And AD is X units. So the first question says determine AK in terms of X. Again, grade 12s, look at the diagram, look at where it is, identify what it is you're actually working with before you go and try and answer this question. So AK is this length over here. Now take stock or take note of where it is. This is in a right angle triangle. So ADK is a right angle triangle. I have X, so I have the hypotenuse. I have a reference angle. I'm looking for the side opposite. I have enough information here to just work with the basic ratio. I don't need to go try and get sine rules and cos rules and all of that nonsense. I'm in a right angle triangle. We stick with the basics. So AK, well, rather, we said this is the opposite. This is the hypotenuse. So I'm working with sine. So sine of 60 is equal to AK, opposite, over hypotenuse X, which means that AK is equal to X times sine of 60. Now we should remember that sine of 60 is a special angle. And so we can actually work out what that is. Sine of 60 is root 3 over 2. So AK is equal to root 3x over 2, or you can write it obviously as root 3 over 2 with x next to it. It makes absolutely no difference, whatever your heart desires. Okay, so we've got AK. Again, I like to write down what I have because I do find it useful, and I know that I'm going to have to use it later on. So this is root 3x over 2. 7.2 then asks us to write down the size of KCF. I initially read that as KFC. Obviously, it's not. So KCF, this angle over here. Now remember, guys, we've been given some important pieces of information. We were told that ABCD and EFCD are rhombuses. Properties of a rhombus: all sides are equal and opposite sides are parallel. So that means DE is parallel to CF. And so what we actually have here are co-interior angles. 60 plus whatever KCF is must give us 180 degrees. So that means that KCF is equal to 120 because of our co-interior angles. Again, this goes back to Lorata's question. No, you don't have to write the reason down, but I feel quite strongly you must because it is a geometric reason. We know we give reasons. Okay, so this is 120 degrees, and now I have that piece of information. So the last question says, it is further given that AKF, I'm going to draw it in for us, for you rather. So this angle over here, the angle between the solar panel and the concrete slab is equal to Y. It is asking us to determine the area of AKF, so triangle AKF. It'd be so nice if I could highlight in some semblance of a straight line. Okay, AKF. Yo, guys, I'm sorry, my skills tonight are shocking. I want the area of AKF in terms of X and Y. So again, think about all of the information that you have already so that we can try and figure it out. Right, it is 7 o'clock, so I am aware of the fact that, again, you guys have exams. I understand that. So what I'm going to do is I'm going to leave that there. You can take a screenshot of it. And then what I'll do is I can put it on Classroom or I can put it at the start of the next lesson. What would you prefer? Just let me know in the chat if you want the answer on Classroom or at the start of the next lesson on Monday. Just let me know and I will do it. Otherwise, take a screenshot and then you can go. Don't study too hard. Start of the next lesson. If anyone feels strongly against that, let me know. Otherwise, I'll put the answer at the start of the next lesson. Lovely, guys. I shall do that. All right, so have an awesome, awesome evening. Good luck with your exams, and we'll see you on Monday. Lorato, before we leave?
Ma'am, I just have a quick question, if you don't mind scrolling up. I think it is wait. I'm trying to also find it on my side. 7.3.
Okay, yeah.
So, ma'am, I wanted to ask, for when you were doing checking if it's a compound angle or anything, if it were to be sine x minus 30, how would you solve for it? Would it be like a different type of a wave from how they're asking us to show that TP is?
It would kind of be the same. So all that would end up happening is you'd now have sine x times cos 30, which is what you have here. And then on this side, it would be cos x times sine 30, which is what you have here. So all it does is sort of swap the terms. So your subtraction looks a bit different, but it doesn't change your methodology.
Oh, okay, ma'am. So it's just swapping the two. That's it. Okay. Thank you, ma'am.
Yeah. Sure. Alrighty, guys. I will see you on Monday. I hope, like I said, good luck for the rest of your exams this week and have a good weekend.